Hi everybody, what I'm going to be showing you today is something that I think is very cool but involves a few different concepts here. We're going to be talking about collisions and conservation of momentum. And you need to remember that some collisions can be elastic or inelastic. We're going to be talking about relativity of velocity and what I think is one of the coolest things in physics, which is symmetry. Okay, so let's go to this problem right here. If I told you that I have two balls of equal mass, and the first ball is traveling towards the second ball at 10 meters per second, the second ball is stationary, they're going to collide, I ask you what the outcome is. Okay, the outcome of this might not be immediately obvious, but you can think about this using symmetry. Okay, so let's look at this situation down here. This is a symmetric situation, and if these two balls are coming into each other, first of all, I want you to think about what the total momentum of the system is. And you should realize this has a momentum of positive 5 mv, this has a momentum of negative 5 mv, and so the momentum of this total system here is 0. Okay, the same as if both balls were stationary. That's something that trips a lot of people up. Energy only adds, but momentums can be negative. Okay, so there's different outcomes in this scenario, but what we know is because they're symmetric going into it, both same mass, both same velocity, that the outcomes have to be symmetric. If they undergo an elastic collision, then their kinetic energy will be conserved. And what that means is they will both bounce away from each other with the same speed. Okay, we know that both balls have to have the same speed because it's a symmetric situation going in, symmetric situation going out. The opposite side of the coin is a completely inelastic collision. And this is where you lose the maximum possible kinetic energy, but of course the momentum of the system is always conserved in any collision. So what we have here is in a completely inelastic collision, you can always identify it by the two objects being stuck together afterwards or touching each other. So I really should have put them next to each other, but they are stationary. And you could fall anywhere along this line. So you could lose a certain percentage of your kinetic energy and then say have a velocity of 3 to the left and 3 to the right, or 2 to the left and 2 to the right. But notice you always have to have this symmetry. You always have conservation of momentum. The conservation of kinetic energy here depends on the material. Okay, and of course, energy really is conserved. It's just lost to friction and heat and sound. Okay, so now that we've talked about that, let's go back to this situation here. This is a situation that we didn't know immediately. It probably wasn't immediately intuitively obvious what the solution is here after the collision. It's not to me. Okay, so I'm going to redraw this picture, and what we're going to do now is we're going to use the fact that actually velocities are relative. So I can tell you from one person's perspective that this is what's going on, but if I have another person on a skateboard who is moving at 5 meters per second to the right, I want you to think about what this picture is going to look like from the skateboarder's perspective. So skateboarder's perspective. I'm going to draw the skateboarder's perspective here. And what you may realize is that from the skateboarder's perspective, he sees himself as stationary. And he sees the right ball approaching him at 5 meters per second. And he also sees the right ball approaching him at 5 meters per second. Okay, so let's pretend this is going to be a totally elastic collision. If it's a totally elastic collision, we know the result because we already discussed it up here. They are both going to rebound at 5 meters per second. But this is from the perspective of the skateboarder. What does this look like from the perspective of the person on the ground? Well, from the perspective of the person on the ground, this skateboarder is really moving forward 5 meters per second. So if the right ball is moving forward faster than him, then the right ball after the collision is actually moving at 10 meters per second. If the left ball from the skateboarder's perspective is moving to the left at 5 meters per second, that means from the stationary person's perspective, that ball is stationary. So that was probably confusing. You just run through that really quick here. This problem's a little bit more complicated. This problem is easier because it's symmetrical. Okay, there's two versions of this: elastic, completely inelastic, anywhere in between. What we're going to do is we're going to solve that original problem using symmetry by thinking about relative velocity, and we're going to assume that this is an elastic collision here in the example I'm giving you. What we're going to do is we're going to view this from the skateboarder's perspective. From the skateboarder's perspective, both balls are approaching at the same speed and the same mass. If it's an elastic collision, they have to bounce back with the same speed. But this is from the skateboarder's perspective. Let's take this situation and imagine it from the stationary person's perspective. And this is the outcome from the stationary person's perspective for a completely elastic collision. What I want you to do for your homework for this problem is I want you to determine from the stationary person's perspective what is the final velocities of the balls if there is a completely inelastic collision between the two, and if there is a collision where 50% of energy is lost. Okay, so I've already done the elastic collision for you. I want you to go through this same logic, but do it in the case of completely inelastic and 50% of energy loss. I'm going to warn you, this does not come to 2.5 in each direction. Okay, when you lose half of your kinetic energy, that does not equate to losing half of your speed, and that's a really big misconception. Okay, so when you are doing this, I want you to think about it in terms of the symmetries. I want you to think about translating into a frame of reference where the situation is symmetric, thinking about what the outcome would be in that symmetric frame, and then transfer back to the frame of reference of a stationary observer. Okay, so this is a really powerful principle. Symmetry is very powerful in physics, very cool, underlies a lot of the really fundamental stuff that goes on in our universe, and we will be talking more about that. Thank you.